Hello dear students. So in today's class we will try to understand various types of forces which are responsible for movement or motion of the atmosphere. These forces are the basic driving mechanism for the transfer of air or the atmospheric mass from one point to another point. In our discussions pertaining to atmospheric circulation, we have seen that warm air rises from the equator and it will go towards the poles. Then this builds up a convection cell which will be mainly responsible for the atmospheric motion. Right. Now we have seen that the temperature of the atmosphere that is driven by the sun is basically builds up this circulation. Right. So in today's class we will try to understand what are the different types of forces which we need to understand in order to be able to successfully understand the motion of air from one point to another point. What are the different types of forces? So let's say to begin with, so any force, forces can broadly be classified into two types. Let's say, so today's discussion is going to be about forces. So these forces, or the discussion that is going to be done in this class, is pertaining to the Earth's atmosphere. Let's say, or more precisely, forces that will act on fluid, mainly, let's say. Okay. So basically forces can be broadly classified into two types, let's say 1 and 2. One is surface forces and the second is body force. So you must have known about all these different types of forces, but let us try to derive mathematical expressions for each of them so that we can combinedly say that our objective, let's say, what is our objective behind the discussion of this class, behind the discussion of these forces, let's say. For example, generally when you invoke the second law of motion, what you realize is that any object, let's say if any object is moving, let's say from rest, and if it is moving, the rate of change of velocity, let's say m dv by dt of this object is equals to the sum of all the forces, let's say sum over I fi. So the objective is, if the motion of this object is to be understood, then the rate at which the velocity of the object changes is equal to the sum of all the forces. So the sum of all forces can be many types of different types of forces can exist. Let's say if you are pulling this object with certain amount of force, let's say F, there is this amount of force that is trying to displace this object from the rest or increase its velocity from one value to another value or change its magnitude. Right. The point is, when this is not the only force, let's say. So in this case, if there is no friction, absolutely no friction on this side, the rate of change of velocity of this object can simply be written as equal to the sum, as equal to this force that you apply externally. But if there is a force due to the friction which is acting in the opposite direction, then you will have to, let's say you call this force as the force due to friction, then you will say that the sum of all these forces is, let's say F minus, let's say Fi. Right. Now the rate at which the velocity of this object changes with respect to time will depend on both the forces. So this is a simple picture in which you can be able to understand what is the importance of understanding or having relations for the different types of forces. Okay, so this is the basic idea. So what we are going to do at the end of this class is that we will be able to figure out how many different types of forces exist in the Earth's atmospheric system, let's say, and what is the role of each of these forces in governing the atmospheric movement from one point to another point. We know very well there are, let's say, before the surface force or body force, we have another type of characterization. This is, let's say, let's call this A. A is, let's say, these are inertial forces, and B is non-inertial forces. Okay, so there are different characterizations of forces. Let's say surface force. Now let's define what is surface force and what is body force. Body force is the one which acts at the center of mass of the object. Let us consider an object, let's say. So this body force will always act towards the center of mass of the object or away from the center of mass of the object. So obviously the body force will depend, so it will depend on the mass of the object. So, the amount of force will depend on the mass of the object. So, this body force, the basic definition of body force is such that it will act at on the center of mass of the object, and the magnitude of the force will be proportional to the mass of the object. So, this force will be proportional to the mass of the object. So, let us say for example, if you are trying to push or if you are trying to pull. So, the force is acted upon the center of mass of the object that you are trying to move, and the amount of force that you apply either to pull or push will always be dependent on the mass of the object itself. Okay. So, here so one example for a body force could be gravity. Gravity is a very good example for gravity for the body force. Okay. So, then the surface force. Surface force is the force which acts at the boundary of the object. So, surface forces generally act across the boundary separating two, let us say, two media or whatever. Okay. So, surface force is the one which acts across the boundary. Let us say for example, so what is a good example? A good example is friction. Friction in the case of solid objects, let us say, and let us say we can viscous force could be an example for fluids. Okay. So, friction which will act across the boundary of the object. So, surface force is the one which will act across the boundary, and body force is the one which acts towards or away from the center of mass of the object. Right. Then what else? So, the magnitude of body force will obviously depend on the mass of the object, and the magnitude of, let us say, the surface force will not depend on the mass. Okay. So, this is the basic characterization by which you can we can characterize the fundamental nature of the force. Okay. Now, in addition to this, let us say, the most easy characterization is, let us say, real forces and apparent forces, or real forces are generally the inertial forces and the apparent forces are generally the non-inertial force. So, generally with your basic understanding of your earlier physics courses, you must be able to tell what is an inertial force and what is a non-inertial force. So, whenever there is the frame of reference that you are talking about, or the object, the frame of reference in which the object is there, if it is an inertial frame of reference, then the forces will be called as, the forces in that particular picture will be called as inertial forces. And if the frame of reference is being accelerated, let us say if it is a rotating frame of reference, so rotating frame of reference may although move with a constant velocity, satisfying the inertial nature to an extent, but if it is rotating, its velocity is changing angularly, right. So, that means that its direction is changing. So, it is an accelerated frame of reference. So, when it is an accelerated frame of reference, you talk about non-inertial forces. Okay. So, it is very important for us to understand that in this picture, in the Earth's atmosphere, let us say, both of this. So, our system is the Earth's atmosphere, the Earth's atmosphere itself. In our Earth's atmospheric system, both of these forces are very much relevant, and both of these forces will be existing to various degrees. Okay. Now, what is a real force? A real force is the one whose effect you can directly feel, but apparent force is the one you see an effect and you do not see generally a force that is causing the effect. Then what you would say is that in order to be able to understand this effect, you say that there is a force which is acting, and this force which is called as apparent force. Okay. So, there can be so the real forces, the examples for real forces are, let us say, one, the real forces. The real forces are, number one example is pressure gradient force. Number two is gravity. Number three, frictional force. Okay, and the apparent forces. Number 1 is the Coriolis force. Number 2 is centrifugal force. Number 3 is gravity. We will see how these forces can be real forces and apparent forces. Okay. Now, what we will do today in our class is that we will try to derive expressions for these various forces, let's say. So, fundamentally what I want to achieve is that if you consider the earth, you have the earth's atmosphere surrounding it. So, what is this atmosphere? This atmosphere is nothing but a fluid layer, right? This is just a fluid layer. Okay. Now, in order to understand this fluid layer, what we do is we consider an infinitesimally small volume of air. This air volume is going to be called as the air parcel. So, what we will do is we will try to understand the movement of this air parcel, the movement of this air parcel. Now, if this air parcel is moving, let us say, its movement has to be attributed to several different types of forces. So, in various cases, in different examples, we will realize that this air parcel's movement is subject to one or all of these forces that I have mentioned here. Okay. So, now in order to write an equation of motion for this air parcel, so my objective is going to be like, I want to write an equation of motion like this for the air parcel. Now, the right hand side is obviously different types of forces. So, let us call this as F1, F2, F3, F4, F5 and F6. So, my objective is to be able to write equation of motion in various situations by combining this F1 to F6 in many different ways. So, that is my objective. Okay. So, fundamentally I want to have mathematical expressions which will represent the nature of these forces and which will also allow me to calculate the magnitude of these forces, right. Let us go one by one. So, the first force, which is fundamentally the most important force in the Earth's atmospheric system, is called as the pressure gradient force. So, this is called as the pressure gradient force. This is generally called as PGF. Okay. Now, let us say, in order to understand, let us consider a volume of air. Let us consider a volume of air, a three-dimensional volume. We take the sides to be of certain dimension. Let us say our coordinate system is like this. This is x, this is y and this is z. Let us say this side is going to be delta x, this side is going to be delta y and this side is going to be delta z. Let us consider a point P at the center of this volume. Let us say this side is being called as A and this side, the opposite side, is called as B. Okay. Now, let us say this is one direction and this is another direction. Okay. Now, so what are we trying to do? We are trying to derive an expression for the pressure gradient force. So, in order to, so this is the pressure gradient force is a surface force. This is not a body force. So, what is this? This is a surface force, and what type of force it is? It is an inertial force. So, it is a inertial force, right. Now, let us say, so what is the idea of force here? I mean, there are atoms and molecules inside this gas volume, right, and they collide and they do some momentum transfer with the walls or among themselves. So, let us say, for example, if there is a momentum transfer with the walls. Now, this volume, what is the volume of this air parcel? The volume is delta x, delta y, delta z. So, what this is going to be called as delta V. Delta V is delta x, delta y, delta z. Okay. Now, if I want this volume to be constant with respect to time, that means if the volume does not change with respect to time, what is the condition that I should imply on this air parcel? I will say that, see, the gas molecules inside this volume are exerting some pressure on the boundary. Let us say, the boundaries are A and B in this case. There are other boundaries as well. So, the amount of pressure that the gas molecules exert on these sides should always be equal to the amount of pressure that the gas exerts from the outside. So, as long as this condition is met, the volume will stay as it is. I mean, the magnitude of this, the number delta x, delta y, delta z will remain a constant, right. So, that is kind of an equilibrium situation where the molecules inside the gas parcel, the air parcel, are executing the same amount of pressure as the gas outside this air parcel, right. So, let us say, what is the idea of pressure here? I mean, fundamentally we have to identify what is the idea of pressure. How does the pressure come into picture? So, pressure, we know very well that force per unit area is the idea of pressure, right. Now, where do we start? We start from the momentum transfer, let us say. So, let us say the pressure at the center of the volume, this center of volume. So, pressure at the center is P naught, okay, let us say. Now, the transfer of momentum per unit area and per unit time, what is the momentum transfer? Let us say d by dt per unit area, momentum is, let us say, small p, by per unit area per unit time is going to be written as 1 by a d p by dt, which is nothing but the rate of change of momentum is the force, and force per unit area is the pressure. So, P, let us say here P is the pressure and the small p that I have written is the momentum. So, what is the idea of force? The transfer, the rate, the change of momentum, the rate of change of momentum per unit area is the pressure. The rate of change of momentum per unit area is the pressure, right. The rate of change of momentum per unit area is the pressure. So, why is the momentum changing? Because of the collisions, right. So, the momentum that is imparted per unit area per unit time is the pressure that is exerted by the gas on the fluid parcel. Okay. The momentum imparted per unit area per unit time is the pressure that is exerted by the surrounding air on the fluid volume delta V. Okay. So, if let us say if the pressure, so here the pressure at the center is indicated as P naught, right. Now, how do you calculate the pressure at a certain point? If you know this is to be the pressure at the center of the air parcel as P naught, how can you calculate the pressure at a subsequent point? Let us say I want to calculate the pressure at the point A. How do you do that? Generally, let us say the simple idea of, let us say, if you know the changes, differentials, so let us say the value at a subsequent point, let us say at a later point, is in terms of, let us say, so I am just writing the relation for your understanding. So, the value at a later point is equals to the initial value at the beginning plus gradient times the change. Okay, so this is the basic idea. So, in that way I can write the pressure at the boundary A as P is equals to P naught plus dou P by dou x along the x direction that you are calculating the gradient, and how much you have travelled delta x by 2, right. So, this is along the x axis. So, the side of this is so delta, so this small dimension is delta x by 2, right. So, in that way, so equilibrium can exist as long as the volume that you have taken delta V. So, again delta V is going to be written as delta x, delta y, delta z. If you want delta V by delta t to be 0, you would require that equal amount of pressure acts from the outside and the inside. Okay. So, let us say the pressure at the, pressure at this, let us say we call it as P Ax and we call it as P Bx on the surface B and on the surface A, which can be written as, so P Ax Pax is the amount of pressure that is exerted by the gas on the wall. Okay, and what is that you have calculated? So P, let us say this is Pa. Pa is the pressure that is exerted by the gas on the wall from the inside. So if you want the volume to be constant, this value has to be same as this value, right? Now, so what will be that? Exactly opposite. So Pax has to be minus P naught plus dou P by dou x into delta x by 2, right? Now, similarly, so what is the, so this is the pressure, the force that is acting here, since you have a unit area, is simply minus P naught plus dou P by dou x into delta x by 2 times delta y delta z. So, because force is equals to pressure times area. So, the area that is going to be relevant here is simply this one, delta x and delta y, delta x and delta y. No, this is delta y and delta z, yeah. So, this, the area of this plate is delta y and delta z, right, delta y and delta z, yes. So, similarly, let us say, so pressure that is acting or the force that is acting on the other side is simply plus P naught minus dou P by dou x into delta x by 2 times delta y delta z. Okay. Now, this is the net, this is the x component of the force. So, here the basically coming back. So, this is the net component of force. So, the force that is existing due to the molecules inside is exactly balanced by the force that the boundary of this volume experiences due to the gas molecules outside. So, if you balance the forces from inside and outside on both the sides, you will realize that the net force that acts along the x direction Fx is nothing but F Ax plus F Bx, which is equals to minus P naught plus dou P by dou x into delta x by 2 times delta y delta z plus P naught minus dou P by dou x into delta x by 2 times delta y delta z. So, then it will get cancelled. We can write, so this will get cancelled. We can write minus dou P by dou x into delta x delta y delta z. So, the net force acting in the x direction does not depend on the pressure. That means, the force that is acting on. So, what is the basic idea? We started from the momentum transfer per unit area per unit time gave us the force, right. Force per unit area, we call it as pressure, right. Now, what you realize is that the force is not proportional to the pressure as it is. Force and pressure are not directly proportional. Rather, force is proportional to the change of the grade, change of the pressure. So, here, so force is proportional to the change of the pressure, but not, or let us say the gradient of pressure along the x direction, but not the pressure directly. So, it will not depend on the magnitude of pressure as it is, but it will depend on the change, the rate at which the, no, not the rate, the gradient of pressure along this direction. So, we have force that is acting on the x axis, along the x axis is proportional to the rate at which the pressure changes across the x axis. Okay, this is a very important relation. I mean, it is not the pressure which drives the motion of air from one point to another point. So, this fundamentally leading to the concept that, let us say, if you consider air mass at some point, this air mass moves from one point to another point. Generally, air mass moves from a high pressure point to a low pressure point. It is natural, right. So, but here it is not the, so if you want some movement ultimately this movement has to be attributed to the force. So, there is a force which pushes this air parcel from high pressure to low pressure. So, this force is not proportional to the magnitude of high pressure or the magnitude of low pressure. How high is it or how low is it? Rather, the force, how much amount of force pushes this air parcel and how much amount of velocity does this force attribute to the air parcel depends on how high is the pressure in comparison to the low pressure. So, this is the force depends on the change of pressure with respect to the x-axis, but not the absolute magnitude of the pressure along the x-axis. Okay. Now, let us say similarly we can derive, I mean the same approach we can also follow for y and z axis, and we can write, let us say we can write fx as, let us say we have already written, minus dou p by dou x into delta x, delta y, delta z. Similarly, we can write fy as minus dou p by dou y, delta x, delta y, delta z, fz as minus dou p by dou z, delta x, delta y, delta z. We can combine these three equations and we can simply write. So, now here delta x, delta y, delta z is the volume, right. Now, we can write mass of this air parcel as density times the volume, right. So, using this into these three equations, we can write them in terms of mass is equals to minus dou p by dou x times m by rho, fy as minus dou p by dou y times m by rho, and fz as minus dou p by dou z into m by rho. Combining these three, we can write force per unit mass is equals to minus 1 by rho times del p. So, what is this force? This force is called as the pressure gradient force. Okay. So, force per unit mass. So, if you consider an air parcel, the force that acts on this air parcel per unit mass will be proportional to the gradient of the pressure, but not the pressure itself. So, density also comes into picture. Okay. So, this is a very important relation which we will need at several instances during this course. So, pressure gradient force per unit mass will depend on the gradient of the force. Now, very important example is, let us say you have a high pressure system and we have a low pressure system. There is a reason why there is a minus here, right. So, high pressure, the movement is from the high pressure to low pressure, right, and the gradient is in this direction, right. So, pressure gradient is in this direction and the movement is in this direction. So, the direction of force will be opposite to the gradient, but will be proportional to the gradient. That is the idea. So, pressure gradient force, let us say, is the basic reason why air mass moves from one point to another point. So, this is the basic idea of pressure gradient force, which is responsible for the movement of air mass from high pressure to low pressure. Okay. So, we will discuss about the remaining types of forces in the subsequent classes. Okay.